אז בואו נעשה את המסורת הקבועה שלנו. רגע, רק תגידו לי שאני לא... איך מורידים ו...
זה שם.
זה? טוב. אז אופיר ואריאל. אוקיי. טוב. אז נזכיר לעצמנו, בתחילת כל שיעור אני אזכיר משוואות מקסוול, בסדר? את הדברים ה... אוקיי, אז בואו תזכירו לי אתם. מה לכתוב? דיב E שווה רו חלקי אפסילון 0, דיב B שווה ל-0, רוט E שווה ל-0, נכון? ובזכות זה אנחנו יכולים להגדיר פוטנציאל, נכון? התחלנו לדבר עכשיו על פוטנציאלים, בזכות הדבר הזה אפשר להגדיר פוטנציאלים, ורוט B שווה למיו 0J, אוקיי? זה המשוואות שלנו במצב הסטציונרי, ואתם זוכרים שאמרנו שבסטציונרי אין את המיזוג הזה בין זמן ומרחב שבעצם מאפשר לי שיהיו לי משוואות גלים, נכון? אין לנו את זה במקרה הסטציונרי, וגם היה לנו את המשולש הזה, נכון? בין רו, V ו-E, ובעצם דיברנו על כל מיני דרכים לעבור מאחד לשני, ואמרנו שעכשיו אנחנו בעצם מתמקמים על החלק הזה, על המעבר בין רו ו-V. ואמרנו שבשביל לעבור מרו ל-V יש לנו בעצם כמה שיטות, נכון? דיברנו על כמה שיטות. אז הייתה לנו שיטה מספר אחת, שזה היה פשוט לפתור את הברוט פורס, אוקיי? את הפוטנציאל. לכתוב שהפוטנציאל זה אינטגרל שאנחנו לא כל כך אוהבים לפתור אותו, של רו n d תו n m 1 חלקי 4 פאי אפסילון 0, נכון? ואמרנו שלפעמים יותר קל לנו לפתור את האינטגרל הזה מאשר לפתור את האינטגרל עם השדה, נכון? אבל עדיין אנחנו מנסים להימנע מזה. והייתה לנו שיטה מספר 2, שזה היה בעצם לפתור את משוואת פואסון או את משוואת לפלס, נכון? מינוס רו חלקי אפסילון 0, או דלטה V שווה ל-0, נכון? ופה בעצם דיברנו על 3 דרכים לפתור את המשוואות האלה, נכון? היה לנו דרך מספר 1, שזה... רגע, אני צריכה לעשות את זה באנגלית. אופס. נכון? כן. אוקיי, so I'm continuing in English, because זה מוקלט, נכון? So we had 3 methods to solve these equations, right? The method of images, and we had the methods of separation of variables. So today we're going to finish this one. And there is a third method which involves the green functions. You remember this from the course with Jonathan? So this is something you will do in the exercise, in the tutorial. I will not cover it during the lesson, the green function, but you will do an entire tutorial only on this. Okay, and these methods, what do they use? They use 2 properties of these equations. Do you remember what they use? They use the fact that there is a unique solution, right? So if you find one solution, it has to be the right one for a given set of boundary conditions. And they also use the linearity of these equations, right? Because for this, for example, we showed that we find a solution, but it doesn't verify the boundary conditions. But then, if we make a large linear combinations of all these solutions, we get something that works. Okay, and there is a third approach, which we will also talk about today, which is to do a multipolar development. Okay, polar development. Okay, so these are the three ways that we approach the potential, that we solve the potential. And today we will finish the separation of variables and we will talk about the multipolar development. Okay, so let's finish the separation of variables first. So what is the last thing that we wrote last time? You have it? יש לכם את הדבר האחרון שרשמנו בפעם הקודמת?
אני מסתכל על המסורת, כאילו בדרייב.
בדרייב? אתה לא רושם? אוקיי. אני ממליצה לרשום, זה מאוד עוזר. יש לך את זה?
כן. כאילו אנחנו בדיוק הגענו לפתרון עם הסכום, היינו לפני שימוש בהטלת.
כן, נכון. So last time, so we finished the separation of variables. Okay, so last time we obtained the following general solution. Vxy is equal to the sum from 1 to infinity of cn's with an exponent of n pi x divided by a sine n pi y divided by a. And then the question became, if you remember, can we choose the coefficients cn's in a way that will verify the boundary conditions? Right? And if you remember, the boundary condition was the following. We had VOY is equal to VOY. Okay, so this is equal to the sum from 1 to infinity of Cn sine n pi y divided by a. Okay, and this is the question. Can we choose the CNs in a way that we will have this verified, okay? And the good news is what? That we can, thanks to the Sturm-Liouville theorem, the good news is that we can have such a linear combination, okay? So we're happy, okay? And the trick here we are making use of a trick. Okay, we're going to multiply everything. Okay, we multiply in order to find what we're trying to do now is to find the CNs. Okay, so we will multiply everything by sine. Do you remember this from the separations of variables you did already? N pi I divided by a, and we integrate. Okay, so we get the following. Okay, so we get that the integral between 0 and a of VOY sinus n pi y divided by a dy is equal to the sum between n equal 1 and infinity of Cn and an integral of what? Tell me.
Sine n pi y a.
N pi y divided by a.
Times sine n tag.
נכון. N tag pi y divided by a dy. Okay, we will call this I, and we can show that I is equal to 0 if n is not equal to n prime, and a over 2 if n is equal to n prime. Okay? Okay, so I'm going to very quickly show it. So if n prime is equal to n, we have that I is equal to the integral of the square of a sinus, y dy, okay, with I've said here b is equal to n pi over a, okay, and here I'm going to use the fact that trigonometric equalities minus, you remember that you can write a square of a sinus like 1 over cosinus of 2, okay, so this gives me, I'm doing it quickly and make sure that you recover it, okay? Check. So this is going to be a over 2 minus 1 over 4b with a sign here between 0 and a, okay? This is a over 2. And if n is not equal to n prime, I'm also going to try to, so I'll tell you what to use, okay? You need to use the fact that sinus x sinus y is equal to 1 cos x minus y minus cos x plus y, okay? And it's pretty straightforward. So straightforward, check, okay? So, and this property, what is this property? In fact, orthogonality, right? So there are two properties that makes things work. The first one is that the set of function of the sinus function is complete, okay? Which means that we can express any function as any continuous function on a given interval as a linear combination of this function, okay? This is the definition of complete. And the other properties that makes this work is the orthogonality of these functions. Okay, so if we go back to hi. יאיר? No. אחיה. אנחנו עושים שיעור פרטי היום. Okay, so if we go back to where we stopped, so we have that the integral between 0 and y of v0 y sinus n pi y over a dy is equal to the sum from 1 to infinity of Cn times this thing. Okay, I've just rewritten this. I'm finishing now the separation of our. So, okay, so I've just rewritten this. Okay, and this we said is equal is either a over 2 or 0, so it's Cn a over 2. Okay, so this is it. I have found that Cn is equal to 2 over a, the integral of v0 y sine n pi y over a dy. Okay, and Vx, V of x and y is equal to the sum from 1 to infinity of Cn exponent npy over a. Okay? So this is the solution. Okay? So this solves it. And as I said, the two things we used are the completeness and orthogonality of these functions. This is something you need to be able to redo in other coordinates too. Okay, separation of variables is that like half of it is just reminding you of things we're assuming you know. Okay, and I just want to remind you that the Laplace equations has plenty of other solutions, right? These just happen to be the solution that verify the specific boundary conditions that we need to be verified. Okay?
Good.
So, we finished the separation of variable. I'm strongly inviting you to do the following table at home. Okay, advice. Populate the following table. Populate the following table. Okay, where you have in 1D, 2D, 3D, and then Cartesian, cylindrical, and spherical coordinates. Okay. Okay. And here the solutions of Laplace Poisson. Okay, so all of these will be products of cosines, sinuses, exponential functions. Okay, there will all be some combination of them that makes your boundary condition work. Okay, and that makes your boundary condition work, and also ensure that what we said last time. Remember that we said that the harmonic functions, the solution of Laplace and Poisson, they are very boring. They don't have extrema, local maxima, local minima. Okay, all their maxima are reached at the boundaries, right? So these combinations, these products will ensure that this is indeed verified. And you remember we said that cosine and sine, we call them harmonic functions often because of the harmonic oscillator, but per se they are not harmonic functions in the sense of solving the Laplace and the Poisson equation. Okay? And I also recommend doing problem number 37 in the Griffith, where there is a demonstration of this. You remember the average property that I told you about last time? That the harmonic functions are such that the value in each point is equal to the local average. This was part of it being boring, right? So there is, and we didn't show it. We just showed it on an example, if you remember, on the straight line in 1D, but in 2D we didn't show it. So in the Griffith, they guide you through a demonstration of this. Okay, so this brings us to the next point, which is the multipolar expansion. So Achia, before you arrived, we said that we actually have several approaches to the potential. Okay, we can solve the brute force integral. We can solve the Poisson and Laplace equations, and then we have all kinds of strategies to do this, which involves some level of guessing, either the images method, separation of variable, which we did now, or the green function, which we will do in the tutorial. And the third approach, which we will talk about now, is the multipolar expansion. And it's very important for the, you will see it involves a lot of calculation, which can be a bit dry, but it's very important. We need it for the next steps of this lecture, where we will be modeling materials. Okay, we will be modeling waves in materials and things like this. And how do we model materials? We basically model the standard materials with many dipoles. Okay, this is the way we will model materials. So this multipolar expansion will be super important for the next step. Okay, so I'm going to start a new. It's still in the chapter about it's still in the hydrostatic chapter, and it's still under the potential. Okay, and here too, it should have a taste of something that you already studied when we will talk about the dipole, but also with some new aspects to it. Okay, so we are in, okay, so 5F is green functions. And this you do in the tutorial. Okay? And this is completely part of the legitimate exam material. Okay, we're assuming that you know it from previous lecture, and we will do a refreshing, but it's part of the legitimate things that we can ask you. Okay, so 5G, multipolar expansion. Okay, so what are the, you heard about this concept before, multipolar expansion? Not the first time? First time? First time you heard it? Okay. So when we do a multipolar expansion, we are actually asking two questions, two related questions. And the question is, how can we express the potential when we stand very far from a distribution of charges? Okay? Maybe you remember last time, or it was maybe in the first lecture, we made one case with, I think it was with the Gauss theorem, when we said, okay, I showed you that if you're far enough, it will look like a single charge, you remember? So there are several aspects to it. Sometimes the question is, okay, how can I express the potential if I'm very far from a distribution which overall the sum of all the charges is 0. Okay, so very far it will approach 0, right? But I want to be able to say something a bit more precise. Okay, so this is one aspect. And sometimes when we do a multipolar expansion, I will also ask you, okay, the total charge is not 0, and still, like, I could approach it with a single charge, but I don't want to do such a simple thing. I want to say something a bit more precise than just saying, okay, very far, it's very similar to one single charge where the value is the overall charge. Understand? But the questions in whatever I'm asking, I'm standing very far from a distribution of charges, and I'm asking, what can I say? Okay? So let's start with a case that you know, which is the electric dipole. Okay? And I will solve this, and then when we solve the multipolar expansion in the general case, I will want you to try to recognize the steps that we did for the dipole. Okay? So make sure that you understand all the steps, and when we do the multipolar expansion, I will ask you, okay, what did we do for the dipole? Let's do it now for the general case. Okay, so we have two charges. You did the dipole in electricity, right? So we have a charge plus Q, and here a charge minus Q. Okay. This is a dipole. This is the definition of the dipole. And here we have distance d. Here we have d over 2. Okay, and we have a point M here. Okay, and here we have R minus. I'm just calling it this way. Here I have a function theta. Okay, here pi minus theta, and this is R. Okay, and now let's write the potential. So I have V of M, which is equal to, you tell me. What is it equal to?
Potential of one charge, Q divided by...
So Q divided by 4 pi epsilon, so plus Q,
yeah,
divided by R plus, right? Okay, and here, doing the superposition,
yes, with R
minus Q. Okay, so Q minus Q, epsilon R minus, right? Okay, so this and this is equal to, I can factor it out to the following. Minus, okay. Now, do you remember the next, so first step, okay, this I'm saying it because I want you to redo the steps in the general case. First steps, I just wrote the potential, okay? Now, do you remember from your previous courses what we do next?
Also was in the homework. So
Okay, so what do we use now? Exactly. So we use the fact, so we use this theorem, okay, that tells me that A, B, C, okay, theta, that I'm using the fact, I'm using this, B cos theta, okay, and we're going to use it in two triangles, in this triangle and in this triangle. Okay, so I can write that R plus is equal to R. So try to make sure that you agree at the same time, okay? D over R cos theta, okay? And if I have now the minus, what will it change? If I have a minus here instead of the plus, where will it change the sign? I will have a plus here. You agree? Okay, and this term, so I've just written the cosinus theorem, and then I'm going to do a first approximation, which when I do the multipolar expansion I will not do it straight away, but the first approximation is to say that when D is very small compared to R, so when I'm very far from the dipole, this goes to 0. This term goes to 0. Okay, so I can write that R plus minus is equal to R1 minus plus D over R cos theta. Okay? And so then I can do a development, okay, because what I need is 1 over this, right? So 1 over r is equal to 1 minus plus d over r cos theta minus, okay, and this, you remember how to develop it? When I have 1 plus x alpha, okay, when x go to 0, this is more or less 1 plus alpha x. Remember this development? Yes. So this, I can write it like this, 1 over r, 1 plus minus d over 2r cos theta, okay? So if I now inject this into this, I get that 1 over r plus minus 1 over r minus is equal to 1 over r d over r cos theta. Okay, and if I put this in the potential, I get that Vm is equal to q d cos theta 4 pi epsilon 0 r squared. Okay? And so when r goes to, so now I have two comments here. First, you see that when we are very far away, v goes to 0, right? And it's also what we expected, because the sum of the charges is 0, and we said it before that when we are very far away, we're seeing one single charge which is equal to the sum of the charges, and the sum is 0. Okay, so this is one comment. The second comment is that you see that this goes like 1 over r squared. Okay, if I had one single charge, how would the potential vary?
1 over r.
Like 1 over r, you agree? So it's true that it's similar in a sense to a single charge, but not quite similar. It goes to 0 faster than if I did have a real single charge. Okay? So these are two important comments. Okay, now let's generalize this and do the general case. And we're going to keep the default here because I want you to be able to recognize the steps that we did just to generalize it. Are there any questions? No questions. Okay. So I was the default, and now general case. Okay, I'm going to draw the situation, and we will keep it. Okay, so in the general case, I have a point O here, and I have a point M here where I will be asking what's the potential at M. Okay, and you remember that we used N to annotate the places where I'm integrating, the places where the charges are. Okay, so here I have some distribution of charge, and I can define a small volume d tau, okay, around each point M of this distribution. Okay. This is M. So this vector OM, I will define it as R. Okay, and this vector, this is OM. So this tells me where I'm asking about the potential. Okay, and ON, it tells me where the charges are. Okay, so ON is equal to r dot by definition. Okay? And the question we are asking is, what is the potential at M? Okay? So, and the approximation I will do is to say that the area where there are charges is much smaller than the distance at which I'm asking about the charges. Okay? And you will see that it's not quite saying that r is larger than r prime. It's slightly, we will have to define this condition a bit differently, but the idea is either to say we are very far away, or the area where the charges are is very small compared to where I'm standing. Okay, these are two equivalent ways to see it. Okay, but let's now start the development, and we will follow the same steps that we did before. So first step we did, what was it? Just to write the potential, right? So let's do the same step. Okay, so step one, we write the potential, and here we cannot write it in the discrete way because I have a continuous distribution. So what will I write? That Vm is equal to what? What's the equivalent?
Integral.
Yes, the integral, exactly. So 1 over 4 pi epsilon 0, okay, of rho n and m theta. Okay, then what was the next step? Step 2. We used the cosinus theorem to write 1 over r plus minus. Okay, so we're going to write 1 over nm. This is what we will do. Okay, so formulate nm, right? You agree? Okay, so and we will use again the cosine theorem. So nm square is equal to r square plus r prime square minus 2 r prime. Okay? Then what did we do? So we wrote the cosine theorem, then we factored out r, right? So let's do the same. So it's equal to r square 1 plus r prime over r square minus 2r prime. Okay, and this we can write it as with a cosine. Here I have alpha. Okay, we write it as 2r prime cos alpha. Okay, so let's do it. So this is equal to 2r prime cosinus alpha over r, right? Okay, so this, so I can write that nm, okay, is equal to r 1 plus r prime over r prime over r minus 2 cos alpha half. Okay, so and previously what we did was we neglected this term, right? I got rid of this term pretty early. But now I will want to keep it because I want to do the development also to higher orders, not only the first order development. Okay? An important thing is that I didn't do any assumption here about the total charge of this distribution. Okay, I'm not saying it's zero. Okay, it's just a distribution. Okay, and now how will I do the Taylor development? What will be the small thing which I will develop? This. Okay, this will be my epsilon. So you see that this condition that I mentioned about standing very far, either standing very far or saying that the distribution is very small, it's the same. It's like saying that this term is very small. Okay? Okay, so I have that one. Okay, so the next step, okay, after I wrote this, the next step was to take 1 over r, right? So let's do it in this case too. Okay, so 1 over nm is equal to 1 over r, 1 plus epsilon minus half, okay? And this, if I do the same Taylor expansion as I did there, it's going to be 1 over r, 1 minus half epsilon, plus 3 epsilon square over 8, minus 5 epsilon cube over 16, plus da da da. Okay, I'm not doing it. Okay. So this is very small. Okay. And if you remember, I can write this in the following shape. Do you remember? I can write it as a linear combination of what? Polynomial of some sorts. Remember this? I can write it as a combination of what we call Legendre. Legendre, maybe? Legendre polynomial, okay? Cosinus alpha. Okay, so these are the Legendre polynomial. Okay? And the general shape of the Legendre polynomial of order L is the following. This I'm just reminding you, okay? dxL x squared minus 1 to the left, okay? Okay, so what did we do next? So in the dipole case, we wrote 1 over r. Then we put it in the potential, right? So let's do the same. Okay, so we're going to inject now this expression for 1 over n, and we're going to put it in the expression of the potential. Just want to check what do I need to reach before the break? Okay. Okay, so let's write it. So V of m is equal equal to 1 over, so this is step, what was the step 4? V over m is equal to 1 over 4 pi epsilon 0, the integral of rho n over r with the sum of Legendre polynomials Pm cosinus alpha d tau. Okay, now the important thing to realize here is what am I integrating over?
Volume.
Yes, but what is the variable that tells me what I'm integrating on? You see what I mean? When I go through all the n's in the distribution, what is the variable that changes? You see what I mean? Like, what is the variable that I'm integrating on?
Small r?
It's not small r, right? Because
And
small r is telling me where I'm standing.
And m.
I'm integrating over on,
Yeah,
right?
that's what I meant.
So it's r prime, right? Okay, so this is okay. So because I'm integrate, so the integral is on r prime, right? And because this is true, I can take many things out of the integral here. Okay, so I can write that this is equal to 1 4 pi epsilon 0. I can take the sum out. Okay, 1 over r. I can take out r out of the integral. R prime m O r prime Pm cos alpha d tau. Okay? Good. Now, here, I haven't done any approximation yet. You agree? Because the sum of the Legendre polynomial is exact. Okay? So I haven't done what I did for the dipole case. I haven't done any approximation yet. And
You assume the epsilon is smaller than 1.
right, but I didn't neglect any term. Oh, right? Yes, I assumed epsilon is smaller than 1, but as soon as I assumed it, I can write this, and this is exact. Okay. Now, now what we will do is the following. I'm going to tell you. So this is the multipolar development. Okay, we will develop it and give it a more friendly shape. But to start with, I'm going to share with you that the first terms of this development have names. Okay, I'm going to tell you what the names are, and for the moment, then they will only be names. And what we will do after the break is to start to try to understand why we gave these names. Okay, so the first, so the term 1, okay, for m equals 0, okay, it goes like 1 over what? 1 over r, okay? It goes like 1 over r, and it's called the monopole term. Okay? The term 2 for m equal to 1, it goes like what?
1 over r squared.
Right? And how is it called?
Dipole.
The dipole term. And the term 3, m equal 2, it goes like what?
R cubed.
Yes. and it's called what?
Are we at the quadrupole?
It's called the quadrupole term. Okay, now I don't have a dipole here. I don't have a quadrupole. We'll see what we mean by a physical quadrupole. But this distribution is not a physical dipole. It's not a physical monopole. I don't know if it's what's the total charge. Okay, but the reason I'm giving these names, can you guess? So in every, I will say it now and we will show it. Okay, so in every distribution, this term will be dominant. The next one will be less. Okay, right? These terms are smaller and smaller. Okay, but for a physical monopole, okay, physical monopole is a case where I only have one charge. Okay, the first non-zero term will be this term. For a physical dipole, we will show it. This will be 0. The first non-zero and so the dominant term will be this. For a physical quadrupole, do you know what's a quadrupole? A physical quadrupole? So we'll see it, but it's actually 4 charges. Okay, where the sum of the 4 charges is 0, but I have 4. So for 4 charges, this will be 0, this will be 0. The first non-zero and dominant term will be this term, etc., etc. Okay, so this is the reason why we give it these names. But the important thing to realize is that these terms exist for any distribution. They don't have to be a monopole, they don't have to be a dipole, they don't have to be a quadrupole, okay? These always exist, with this one being the dominant, this one being the next dominant one, etc. Okay? And it just happens that for these physical animals, these are also the first non-zero terms, and we will show it. Okay, so hesitating. Let's do another 5 minutes, take a break of 10 minutes, and okay, and do another 15 minutes. Okay, so now what we want to do is to write V in a more explicit, okay, with this, this is a nice way of writing it, but we do want to write it in a way that looks more like what we did for the dipole. Okay, we want to develop it and look specifically at each of the terms. So Vm is equal to 1, 4 pi epsilon 0. Okay, so here I have 1 over r with O r prime ditto, okay, plus 1 over r square r prime cosinus alpha O r prime ditto, okay, plus 1 over r cube r prime square 3 half cosinus square alpha minus half O r prime ditto plus many other terms. Okay? And this is the monopole term. Okay? This is the dipole term. This is the quadrupole term. Okay? And now what I will want to do is to write the these two terms, the dipole terms and the quadrupole terms, with an additional quantity, which in the case of the dipole is going to be the dipolar moment. You remember this? Remember the?
I remember the name.
Okay. So we will define it, we will introduce it, and we will reformulate this term with the dipolar moment, which is going to be super important for the next lectures. Okay, and we will also introduce another quantity which is called the quadrupole tensor, which is the equivalent of the dipole moment, which will also help us reformulate this. Okay, this is what we will do now. So, okay, and I'm going to name them with letters. Okay, so this will be A, this will be B, and this will be C. And from now on, I will focus on these three terms. Okay, I will not go to higher orders in the development. Okay, so I'm going to leave this small drawing. Okay, so let's look at the first term, the monopole term, okay, which for a distribution, for a random distribution about which I don't know anything, this term will be dominant, okay? Okay. Which is dominant for a random distribution. Okay, so A, okay, is equal to the potential of the monopole. Okay, this is how I called it: 1 over 4 pi epsilon 0, 1 over r, or r prime d rho. Okay, and this is equal to what? This is just the integral of the charge density. Okay, so I can replace it by what? By the total charge. You agree? So this is equal to Q over 4 pi epsilon 0 r. This is the total charge. Total charge. Okay? Now, what is the only case in which this is equal to the potential? If I want the potential to be equal to A,
If R is very big.
Okay, in what case will V of M be equal to A, to this?
Q is not 0.
What?
When Q is not 0.
Right. And also when all the R primes are 0, right? Because I need all the other terms to cancel, right? So the only case in which V is equal to the monopole terms is when I have a monopole at 0, a single charge at 0, right? At the origin. Because if I have one charge which is not at the origin, I will have a dipole term, right? Because there will be a R prime in the development. Yeah, you agree?
Yes.
Okay, so
but it will be much smaller, no?
it will, but what I'm trying now is what I'm asking is exact. Like, when is it exactly? Okay, so the only case where V of M is equal to V mono, okay, is a point source at the origin. This is what we call a physical monopole. Okay? So, for a physical monopole, the potential is equal to the monopole term. Okay? Okay, because the R prime cancel. Okay, and what did we do? I reformulated the term, okay, and then I said for a physical monopole, what will it be? Okay, and now I will do exactly the same for a dipole and a quadrupole. Okay, I will, for the dipole term and the quadrupole term, I will reformulate the dipole term, okay, in the general case, and I will use, so I cannot use the total charge, I will use another definition, I will use the dipole moment, okay, and then I will ask, okay, this is in the general case. In the case of a physical dipole, what can I say? Okay? And for a quadrupole, I will do the same. I will reformulate the quadrupole term with a third tool, which is the quadrupole tensor. And then we will say, okay, let's step backward. What do we have for a physical quadrupole? Okay? Okay, so let's look at B. Let's look at B. Okay, which is the next dominant term after the monopole term. Okay, so B. Deep. Okay. This is equal to 1 over 4 pi epsilon 0, 1 over r squared, r prime cosinus alpha, rho r prime d tau prime. Okay? And I remind you that we can write r prime cosinus alpha like ER one second. So this, okay, I can write it as the product of a unitary vector in the direction of r prime. Product ON, do you agree? Because this ON is going to be r prime, here, okay? It's ER, sorry. Right? If I have a unitary vector here, ER, and I do the product with ON, okay? So this allows me to write it in the following way. I can write that V dipole is equal to 1 4 pi epsilon 0 ER divided by r squared, and then the integral of the volume integral of ON rho r prime, it's rho of ON d tau, right? Okay, this is r prime rho of r prime, right? Now, what is this thing? Okay, this is equal by definition, this thing. This by definition is the dipole moment, okay? Dipole moment, okay? Maybe you remember it from, we do a parenthesis, when you did the dipole, you had n minus, n plus, okay, minus q plus q, and p is equal to q o n minus q o n plus, No. This, okay? And this is equal to q n minus n plus. Okay, so this is the way that you saw it. Last time you heard about the dipole moment, you saw it in the context of a dipole. But it's important to realize that the dipole moment is defined for any distribution. Even if I have one single charge, okay, I will have such term. If I have one charge that is not positioned at the origin, this distribution will have a dipole moment. Okay? So P is the dipole moment, and so I can write that V dipole, okay, is equal to P ER divided by 4 pi epsilon 0 R square. Okay. And this, what does it depend on? If I have a distribution, it depends on the size of it, on the shape of the distribution, on the density of charges of the distribution, right? So this is really a character. This really characterizes the distribution. Characteristic of the distribution. Okay, it depends on the density. It depends on the shape, on the size, etc. So this is really a property of the distribution. Okay, and I reformulated the dipole terms in terms of this dipole moment, and you see that in the case of a dipole, okay, this is what we said earlier. In the case of the dipole, the monopole term will be equal to what? 0. And the first non-zero term and dominant term will be the dipole term. Okay? Okay, so now let's ask what is the dipole moment of a quadrupole. I remove this. Okay. I wasn't planning. Okay. It's okay. So now let's ask, in the case of a physical quadrupole, what will B will be equal to. Okay? So let's look at a physical quadrupole. We'll define it. So a physical quadrupole is 4 charges, and 1 and 2 and 4 and 3. Okay? And it's like 2 dipoles, but they are לסירוגין. Okay? It's like 2 alternating dipoles. Okay? So you can see either like 1 dipole and 1 dipole, or like this. Okay? Okay, so in the case of a quadrupole, what will A be equal to? A is equal to what? To 0, because the total charge is 0, right? Now let's look at B. So let's calculate P. So P is equal to Q O N 1 plus
With O.
O, it can be anywhere, okay, so ON1 plus QON3 minus QON2 minus QON4. You agree? Okay? And this is equal to Q N4N1 plus N2 N3, right? So N4 N1 plus N2 N3 is equal to
0. Also 0.
0. Right? So for a quadrupole, for a physical quadrupole, the first two terms are 0. And you're guessing what I already said, that the first non-zero term for a physical quadrupole will be the quadrupole term, and this is why we call it the quadrupole term. Okay? Okay, so what we will do now is to write in the same way that we wrote B in a more compact way using the dipole term. We will now write C, the quadrupole term, in a more compact term, in a more compact way using the quadrupole tensor. But before this, I want to do a small table, which I will do here. Okay, so I'm hesitating. Maybe I will do it here. So, I have general case. I want to write the three terms that we're talking about in the general case. In the case of a physical monopole, you know this phi, it means it's a Greek letter, but I'm using it. Okay, let's write it. So, this will be a physical monopole. A physical dipole. And physical quadrupole. Okay, so in the general case, this is the monopole term we saw is equal to Q over 4 pi epsilon 0 R. Okay. So in the case of a physical monopole, this is non-zero, right? Then this is non-zero and it's the dominant. Okay, I'm summarizing things that I said already. Then the dipole in the general case, I can always write it in the following way: P E R, okay, I'm using this, over 4 pi epsilon 0 R squared. Okay, so in the case of a physical monopole, what do I have here? Only if the charge is at the origin, right? If the charge is not at 0, there will be a dipole term here. Okay, this is an important point.
You're talking about physical monopole right now.
Right.
So it's supposed to be 0 for a physical monopole now.
If I put a charge here in N and it's not at 0, a distribution with one charge that is not at 0 will have a dipole term. It will not be dominant, but it will exist. Okay? So it's 0 if the charge is at the origin. Okay, if the charge is not located at the origin, this term will not be 0, but it will also not be dominant. Okay, so I can neglect it maybe, but okay. Okay, now in the case of a physical dipole, what is A? 0. Okay. And in the case of a physical dipole,
Non-zero.
מה?
Non-zero and dominant.
Non-zero, dominant. Okay? And I'm also going to remind you that P is going to be equal to this, okay? Just so that you have it in mind, but yes, the important thing is that it's non-zero and it's dominant. And what did we do here? We just showed this column, okay? So we showed that for a physical quadrupole, A is 0, right? We just showed that B is also 0, okay? And the next thing I will do is to show you that for a physical, okay, maybe it's not the next thing, but I will show you in a few minutes that for a physical quadrupole, this is non-zero, okay? And we will formulate it with the quadrupole tensor. Okay, so this I said. So this, okay, so otherwise, V will be very close to A, but B is non-zero. Okay, this is an important point. And before I move on to the quadrupole, there is one more thing that I want to show you. Okay. Just checking that it's the last thing I want to do. Okay, so the only situation when P does not depend on the origin is when so the only situation when does P does not depend on the origin? We know that for a dipole it does not depend on the origin, right? Because it's equal to q n minus n plus. It doesn't depend on where I've put O. Okay, for a quadrupole I know it's 0. So you can guess that the cases when the dipole moment does not depend on the origin are when the total charge is 0. Okay, is when q tot is equal to 0. Okay, and we can show it very quickly. Okay, if you need to do a change of variable. If you have a coordinate system like this and another coordinate system like this, so y bar, x bar, and y x, and this is O bar, okay, and this is a small d tau, okay, and this is a vector A, and here I have R bar prime, and here I have R prime. Okay, so you can show, do it very quickly, that P bar, okay, which is the P in this system of origins, of coordinates, this is equal by definition to R bar rho R bar d tau, okay, which is equal, I'm writing it now as a function of R prime of the other coordinate system, rho R prime d tau, okay, which is equal to P minus AQ. Okay, so P is going to be equal to P bar only when Q is equal to 0. Okay, so the dipole moment does not depend on the origin, only for distribution where the total Q is 0, and so and this is why for a monopole it's going to depend on the origin. Okay. Okay, so now let's do the same thing which we did for B, the reformulating B in terms of the dipole moment. Let's do it for C, and what will play the role of the dipole moment is the quadrupole tensor. So I will define the quadrupole tensor, but let's first let's start by rewriting C. So C was equal, if you wrote it down, to the following. It was equal to minus R prime square, and here in the next few minutes, it's really important that you try to do the calculation together with me, because otherwise it's just going to sound to you like a long dry calculation and boring calculation. It's important that you try to follow it together, okay? So this was C. Okay, you need to check that. So earlier I wrote it with cosines, right? So make sure that you agree. Okay, make sure at home. Make sure you agree that what we previously wrote as defined as C is equal to this. Okay. Okay, I'm doing something very similar to here, where I said that R prime cos alpha is AR ON. So, okay, in a similar way, you can rewrite C like this. Okay. Okay, and now we'll start working. We'll write this in Cartesian coordinates, and I will define the tensor in Cartesian coordinates. So R is OM by definition, okay, and I'm going to define it like XYZ, and R prime is by definition ON. I'm going to define a set of coordinates for it. Okay, and now let's take, sorry?
This is the specific coordinates of the vectors?
Yes, I'm just defining some coordinates. Okay, and what I will want to do is rewrite C in terms of these coordinates. This is what I will do in the next few minutes. This I will keep. Okay, so I remind you that my goal now, I have two goals. My first goal is to write C in a more compact way, okay, in the exact same way that I rewrote B using the definition of the dipole moment, same way that I rewrote B, which wasn't very beautiful, like this, I want here a compact way of writing C, okay? And the equivalent of P will be the quadruple tensor. And then the other things, my other goal is to show you that for a physical quadruple, what I said now didn't have to do with the physical quadruple, okay? I will always be able to write C in this compact way, but then the next thing is, okay, if I look at the physical quadruple, I show that A and B are 0, and I want to show you that C is the first non-zero term, and it's also the dominant one, okay? Okay, so let's now, because we have a lot of calculations, I want to make it try to make it as organized as possible. Okay, so I'm going to start with this term. Okay, and then so I'm going to rewrite this term with my coordinates, okay? And then I will write this term. Okay, I'm not dealing with the coefficients now, just to not make it more complicated, but I want to write the green and red components in terms of their Cartesian coordinates. Starting is, let's rewrite the red one. No, the green one. Okay. Let's do it. So R prime divided by R4, okay, is equal to x prime plus y prime plus z prime. And the square here. Okay, I forgot a square. I forgot a square. 1 second. Yes. Here there is a square.
Can you repeat why this is the general case?
Why this is the general case? So when I wrote earlier the development of the
With the Legendre
potential with the Legendre polynomial, I reached this. I reached something very similar than this, but where I had cosinus of alpha,
yes.
And then in the same way that I did for the dipole, I used the fact that, okay?
Yeah. So maybe also a plus sign.
What?
It's plus 3.
Yes. It's a plus here. Right. Alright. Yes, this should be it. There is a 3 and a 2. Yes, that should be it. Okay, so this square divided by R4. Okay? And this, so now we're going to cheat a bit. Okay, I could have tell you, find me metrical way of writing this, okay, and you could have find it, but now I'm just going to give you the answer, and you will have to check at home that you remember how to do a matrix product, so we'll just have to check that you agree, okay? So this is equal to 1 over 4 squared x, y, z. And now I'm giving you this matrix, z prime x prime, and you will need to check at home that you agree with this. Prime, tac. Okay, and it's something that you could have found, but just to save time, I'm giving this to you. Okay, so this, convince yourself that it works. Okay? Now, let's rewrite the red term. Let's rewrite the red one. Okay, so and here I'm going to do the same. I'm going to give you the metrical expression for it. So this is equal to x prime square plus y prime square r square. Okay, and this is equal to 1 over R4. Okay, I can put an additional R square here. And these two, you will have to convince yourself that you agree. Now I'm also going to write the big and ugly matrix here. So x prime square plus y prime square plus z prime square. 0, 0, 0, 0, x prime square plus y prime square plus z square, 0. Okay. Okay, now let's add the coefficients. Okay, in C, these two terms are added. So this you have to check. Convince yourself. Okay, now let's add the coefficient, right? In C, it comes in the terms of 3/2 of R prime divided by R4, right? Minus R prime divided by 2R square, right? We have the coefficients.
Square.
2R square. Yes.
So R prime square.
R prime square. Right? Okay.
Okay.
And this is equal to 1 over 2R4 x, y, z with a big matrix here. Okay, and here too I could give you, just as an exercise, you have to put a coefficient here, another coefficient here. I'm going to give it to you, but just make sure that you agree, okay? So the x prime square minus y prime square minus z prime square, and here I have 3 x prime y prime and 3 x prime z prime. Okay, you see that there is a logic to it. Okay, here I have 3 y prime z prime and 3 z prime x prime, 3x prime y prime, and here I have 2y prime square minus x prime square minus z prime square, and here I have 3y prime x prime, and here 2x prime square minus y prime square minus z prime square. Okay, this is the matrix. Okay, now I will define the tensor, the quadruple tensor, and it's a bit unfortunate that the way to annotate it is Q, okay, like the total charge, but it's not the total charge. It's the quadruple tensor Q, not the total charge. Okay, so this by definition, okay, is equal to, so this matrix here, I'm calling it A, okay, is equal to the integral of A rho r prime d tau, okay, and this tensor, so when you do a general relativity, it will be defined in more rigorously, but for us a tensor is just a matrix, okay, and so Qij, the term, the ith and jth term of this matrix is the following. It's equal to 3 r prime I r prime j minus delta ij I prime square, right? You agree that this is just a way to write the I and j term of this matrix? R prime d tau. Okay, and so this allows me to rewrite the term C Okay, I remind you that my first goal was to reformulate the term C in a more compact way, like I did for the dipole. Okay, so V x is equal to 1 over 4 pi epsilon r epsilon 0 r5 x q x. You can put a transpose here. In the tensor calculation convention, we don't have to put transpose, but I'm putting it, okay? Just to facilitate things. Okay, so C, this is C in the general case. Okay, so in the same way that sorry. So C is equal to this term, okay, where by definition, okay, xqx is equal to sum between 1 and 3 of xy qij xj. Okay, so I can put it here. What's the time? Because I turned like 9:55. Okay, so in the last 5 minutes, I will just take a last calculation effort to put it in this shape. Okay, where I will also have ER appearing here. Okay, so Vx is equal to 1 over 4 pi epsilon 0 r square 3 times half of x Do you agree with what I did here? I added here r square. Okay, I wrote r5 like r square r to the cube. Okay, and I made this appear. Okay, and this is equal to ER, right? Because it's OM over the norm of OM. Yes? So I can write this, okay, like 1 over 4 pi epsilon 0 r cube half of ER Q ER. Okay, so this is C in the general case. Okay, 1 over 4 pi epsilon 0 r cube half of ER Q ER. Okay, and you should keep in mind that here you can put a transpose if you want, but we don't have to because this is how we define tensor calculation. Okay, and so in the general case, okay, in the most general case, and I have, so general case, I have that VR is equal to 1 over 4 pi epsilon 0 Q over R plus P ER over R square plus half of ER Q ER over R cube. Okay? This is my multipolar development in the most general case. You agree? Okay, and what we will do next time, because I didn't have time to do it, is to show you that in the case of a physical quadrupole, this is 0, this is 0, but in the case of a physical quadrupole, this will be the first non-zero, and so also the dominant term. Okay?
תודה רבה.